My name is Carl Pearson. I'm a PhD student with Professor Hu in the Electrical and Computer Engineering Department. Professor Lumeta asked me to give a guest lecture on some of NVIDIA's performance profiling tools. That's Nsight Compute and Nsight Systems. I think it will help you in your course projects to take advantage of some of these tools, both in order to improve the performance of your code, but also to be able to explain why your code performs the way it does. So the main purpose of this lecture is we're going to talk about sort of the CUDA ecosystem of tools for understanding GPU performance. And there's also some insight into the performance of the system, meaning maybe the CPU and what it's up to, but kind of only as it relates to GPU utilization. So we're not really going to talk about other performance tools that you might have used in other classes or be familiar with, gprof, perf, vtune. If you're curious about those, you can look them up. To some extent, they may have amount of GPU support, but I'm really just here to talk about the NVIDIA performance tools. So to that end, I'm going to talk a little bit about profiling in general. And then the tools support a variety of different ways for profiling. I'm going to talk about a specific one that is useful to us that you can use through Rye. If you have access to GPU in other contexts, feel free to explore how to use the tools in those contexts to help you with your profiling. I think this will be a good starting point for that. There's some modifications you might want to make to your code at compile time, both compiler flags, but also maybe some changes to code to the actual code that will improve potentially the quality of the results or make it more useful. And then we're going to go into some of the actual techniques for measuring performance. So before we even really talk about profiling, I wanted to talk about using something called CUDA events to measure performance. So this would be how you would measure the time of certain operations in your program at a high level. Then I'm going to give you a quick reminder about matrix multiplication, just because we're going to use that as the example for the profiling and I want it to be fresh in your mind. And then I'm going to really talk about the two tools and walk you through how to interpret some of the results and understand it. Those tools being Nsight Compute and Nsight Systems. Everything that I use in this lecture is available on GitHub. There, you're free to use it however you'd like, whether for this class or in the future. I just ask that if you do use it for some other project or some other way, that you give some kind of attribution just like you would anything else that you do. So this includes showing you how to add the performance tools to Docker images. You can use it as an example. You can use those Docker images for your course project maybe. There's the sample matrix multiplication code is there if you want to look through it or see how it works or modify it. There's the Rye build there also for you to submit it to Rye, so you can also submit these results that I'm seeing and go through them yourself. But of course, you can just build these code and profile them on any system that has CUDA. Obviously, the performance can vary dramatically from what we'll present here, especially if you have a consumer GPU and not a workstation or server class GPU. They can have very different performance profiles, but you're free to do that if you'd like. So I want to draw a distinction before we really begin about different kinds of profiling. So one question that I think we think a lot about in this course is, how fast is the GPU going to execute my kernel? And this is such an important question that there's a tool that NVIDIA makes dedicated solely to this question, and that's Nsight Compute. So we'll talk about that. But there's sort of a higher level question, which is how effectively does the system deliver work to the GPU? What is the system doing while the GPU is working? How fast am I getting data to and from the GPU? When I have the CPU do some of these things to control the GPU, like launch kernels, how long does that take? If I tell the GPU to do two things at once, does it actually do two things at once? These are all questions that are answered by a separate tool called Nsight Systems, which I'll talk about at the end. So the profiling model that we're trying to support here is one where you, the listener, are what we might call a client. So you're developing on a computer without a GPU, or it has the wrong kind of GPU. You control some sort of target platform which has the right kind of GPUs, the right number of GPUs, maybe through SSH or something along these lines. And then if you need to transfer data between these two systems, maybe you have some kind of network file system or file share, you use SCP or something like that to move data between the two. So this is a very common GPU development model in the real world. Even if you're deploying things in a virtualized cloud environment, if you're really doing GPU performance, you'll probably have direct access to some kind of development environment, but you won't be sitting in front of that computer actually working on it. And so for our course projects, of course, as may have been explained to you, we have sort of an approximation of this system with Rye. So you, on your laptop or maybe in the EWS lab, create a project directory and specify it with Rye, which runs on this target platform. And then you can download anything from that target platform back onto your laptop to be evaluated. So this is the kind of profiling that we're trying to support. So there are other ways to use these tools to do profiling, but I'm not really going to talk about those in this lecture. So to that end, we're going to do sort of a two-phase profiling approach where you record profiling data on the target as your application executes there, whether it's with NSYS or the Nsight compute, depending on what you're trying to do. Then that will generate some files, which you will copy back to the client by downloading the Rye build directory, and then you'll open up the GUI for Nsight systems or Nsight compute on your laptop on EWS, load up those result files, and see what the performance was like. So the profiling in this case is not necessarily interactive. You can't make a change, run it, and have the results automatically show up in your profile. You'll have to re-download these files, reload them in the profiler to see the results. So I mentioned there's some things that you might want to do to prepare your code for profiling, and obviously you can do this at any time. One thing that requires some changes to the CPU code is something that we can call host code annotations. So basically NVIDIA allows you a way to mark particular regions of your code, and they'll show up in the profiler under particular time spans. So you can say, oh, I really care about the part of what's going on the system when my host code is doing this, so I can mark this particular range, and it's easy to see it in the profiler. To do this, you have to annotate your host code a bit, so you'll include a particular header, this nvtool_ext header. That should probably be lowercase nv, and you'll have to also link against this library. But then you can use this nvtx_range push to add a span to your code, and nvtx_range pop to remove that span. And this is like a stack, so you can push twice and then pop twice, and you'll get nested spans that show up. And we'll see that towards the end of the lecture, an example of that. One other wrinkle that I've seen students in 408 struggle with is that if you introduce some kind of subtle error, some kind of undefined behavior that doesn't cause your kernel to necessarily terminate under normal circumstances, it can cause errors during profiling, especially if you are allocating memory on the GPU and then writing outside the bounds of that allocation. I think this is because profiling often requires additional allocations outside the control of your program to store various parameters and things that are later returned to the CPU to be recorded. And if you write outside of memory that you've allocated, you can trample over some of those structures and cause the entire profiling process to get corrupted. So if you think that your code seems to be working but the profiling crashes or provides some other error, my advice to you would be to run your code with this tool called CUDA memcheck. This is a tool that automatically instruments your code when it runs to check if all of your array accesses are in bounds and things like that. It makes your code execute a lot slower, but if you see any errors in there, fix those and then try the profiling again. So, in short, make sure your code is standards compliant before you try to profile it. Otherwise, who knows what will happen, right? Undefined behavior. So the second thing you need to do is change the way your code is being compiled. So when you're doing the profiling, you want to compile your code with optimizations. Otherwise, the performance is not realistic, especially since debug code often has many more memory references than optimized code. The CUDA compiler applies optimizations to device code by default, but what you'll want to do is if you were compiling with this -G flag, which introduces debug information into device code, you'll want to remove that. The way we get some useful information in the device code but still allow all these optimizations to occur is with the -line-info flag. This allows you in the profiler to correlate certain things back to the source code, which makes it easier to understand what's going on. So I'll show what that means later as well. But basically when you're compiling, you want to get rid of this -G flag and you want to add this -line-info flag instead. Typically when I'm writing code, I just always compile with -line-info. It doesn't really hurt the performance, and it makes debugging and some stack traces a lot better. So just as an example of what this does, sort of in the assembly code, it will insert these little markers that basically say this next region of the assembly code was created from a particular location in the source files. And so I've just pulled this example out of the assembly code for the matrix multiplication. And so it's basically just saying you can see that in the compiled PTX on the left, it's moving the CTA ID and the thread ID into these various registers, which is exactly what we're trying to do in the CUDA source code. And then it's doing this multiply and this addition of those three registers together in order to produce this global ID. And so that .loc operation just is not an instruction that's executed. It's just debug information so that when we're visualizing this side by side with the source code, the tool can draw the connection between the PTX and the source code for us. So that's all that line info does. There are a few other flags that look like they might be relevant for profiling, but they are not. So this profile flag is for a different profiling tool, so don't use that. This debug information for host code, we don't need that for profiling since we're only looking at the device code. And especially this device debug we want to avoid because it will screw up the performance of our device code. The final thing that you'll want to do is see if the Nsight system is able to get the information that it wants from your system. Otherwise the profiling might not work. You don't have to worry about this in Rye, but if you're trying to profile on another system, you will. So basically you'll run this particular command and it will tell you whether it thinks the configuration is okay or not. If it's not, you'll have to consult the documentation for how to fix it. But this is just an example of what we expect to see. So the kernel needs to basically be permissive enough to allow an application to query some of these various parameters. It needs to be a supported kernel version. It needs to be able to hook into particular sampling triggers and things like that. So this is just, if the profiling doesn't work for some reason or doesn't have the information that you're expecting, this could be part of the reason why. Again, though, on Rye, you don't have to worry about this. We have it set up for you. So one wrinkle to all of this is that profiling will affect the performance of your code. The timing of the operations while you're profiling them will be distorted, sometimes a little, sometimes a lot. So we use profiling to improve the performance of a kernel, but then whenever we're trying to report the actual performance, you don't want to look at the profile. You want to run the code on its own with a few CUDA events used to time the actual operations when they're actually running. So that way the operations themselves are not disturbed. So, like I said, you can follow along yourself. What you're going to want to do is clone the repository, and then you'll go into the sgem folder in there, and that's the project folder you want to submit through Rye. It will do a great many things. It will compile and run all of the code and create all of the profiling files. So once it's done, look at towards the end of the output, and you'll want to download that compressed folder that it tells you about to your client and decompress it, and then those are the files that you will be able to open up in these different tools. So you can pause here in order to do all that. Then, now that you've come back, you'll also need to make sure that you have Nsight Compute and Nsight Systems installed on the client system. So whether that's your own laptop or EWS. If you have CUDA installed, they should already be there. But in any case, you can get those set up too. If you don't have them, you can just follow along through the slides. If you want to follow along, pause here and try to do these things before carrying on. Okay, so as a reminder, we're going to use dense matrix multiplication as an example. So in this example, we're trying to multiply matrices A and B to produce C. And on the left, I've sort of highlighted the row and the column that correspond to a particular output of C. So we dot row I with column J to produce value I, J, and C. And in this particular case, we want to recall that each entry of the AB matrix is loaded from global memory multiple times, because any entry in the same row of C will all require all of the values from that row of A. So each of those threads will load the entire row of A, in some sense redundantly. So we had a partial fix for this problem, which was shared memory tiling, where we tile A and B so that instead of doing those repeated loads from global memory, we instead get to do them from shared memory, which is much faster. So then we have to use these tiles and march down the row and the columns, sort of computing partial products one tile at a time before we write them out to the final product matrix. And we don't talk about this in 408, but there's something called joint shared memory and register tiled matrix multiplication. So registers are extremely high throughput, even more than shared memory, right? When we're accessing registers, right, it might be a common instruction to add two 64-bit operands to produce another 64-bit operand. So we're talking about, 3 64-bit operands per cycle per thread, maybe even more operands than that for some instructions. The problem is that these registers are private to each thread. So in order to use the registers to capture any data reuse, like we did with shared memory, the thread has to produce multiple output values. When we use shared memory, which is quite high throughput, but maybe not as high as registers, right? We can have the thread block, collaboratively load a tile of global memory into shared memory, and then multiple threads can make use of those loads out of shared memory. With registers, we can't do that because registers are private to a thread. So we have each thread produce multiple results from shared memory, or produce multiple results of the output using a single register value. You can look at the implementation of this code, but you don't really have to be able to reproduce it for 408. But basically the gist of this is we will load tiles into shared memory for matrix B, but instead of doing shared memory tiling for A, we will do register tiling for A. And each thread will produce tile size B results of the product matrix instead of a single result. So to try to make this a little bit clearer, for a particular set of 3 results on the right, we're going to have to load 3 columns from B and a row from A. And we're going to do the same sort of iterative approach with tiles that we did in the tiled matrix multiplication. So as an example, right, the first tile is the top chunk of that column of B and the first slice of that row of A. And so that chunk of the columns of B will be in shared memory, and those 2 values from the row of A will end up in registers, but only one at a time. And so then we're going to compute these 3 partial products from those 2 values of A and 6 values of B in this example. And that's what's going on in the top right of the slide. So first we're going to load one value from A, and we're going to reuse it 3 times for the first row of the shared memory of B, and then we're going to load the second value from A and use it for the next row in the shared memory of B. So every thread in this thread block gets to reuse those values from B, through shared memory, but they get to reuse their values in the A register as well by using multiple values from the B shared memory to produce multiple outputs in C. Like I said, we go over this quickly. You're not required to understand it for 408, but basically what we're doing is we're moving some of the memory accesses from shared memory to register, which is even faster, in hopes of getting even more matrix multiplication performance. I'd encourage you to look at this code to see how it works. So this is just sort of a summary of where the reuse comes from. So we don't have any reuse in the basic matrix multiplication. Per block, we're going to produce 1024 results because we have a 32 by 32 thread block. We don't use any shared memory, and we use 1024 registers per block to create the product matrix values, right? Because each thread is creating one product matrix value. So the same is true in the tiled matrix multiplication, except now we get to reuse each of the loads from global memory, tile size times. So if they have 32 by 32 tiles, we get some reuse, so we reduce the amount of accesses from global memory to produce the same product data. But we have some additional shared memory costs now because we have to store a tile of each matrix in shared memory. And then so now we can see the joint tile. The joint is kind of a mix between the two. It uses more registers because it stores parts of the A matrix in registers. But it uses some shared memory because it stores parts of the B matrix, but it doesn't use a lot of shared memory per block. And the blocks are smaller to produce the same amount of product data because each thread in the block produces multiple outputs. So we only need a block of 64 threads to produce 1024 product values. So for the first part of our code here, we're going to look through we're going to be consulting three of these files. They're shown on the slide. They're the 11, 12, and 13. Basically, these files are mostly focused on kernel time. So they're going to create data on the host, move it to GPU, then repeatedly do a matrix multiplication, and then move the result back to the host to possibly check it. So here we're really just examining the kernel performance by running the kernel multiple times.